So is that, yeah, so pretty straightforward. It was a pain in the ass on the right side. We needed the 50 when it was more power. I could finally do the 60 power. Yeah. It was 15 things. Well, yeah, I found the 40 more finally. But it had some really big like what it is. Use a stick. Yeah, that 16 will never get into full power. It's still like this one. Transmission is not new, so. Weird little way.
Thank you. I'm sorry. Oh, I got but I like to know what I got yesterday. Yeah.
If you're in a earlier. I look at it. Hard to do. And so. She's such an insight on the business. What?
Hello, good morning. I posted a new homework. Expected to be another homework in between. Homework 5 and I will decide on the dates. I hope you do feel or you felt that the current homework that was due today was relatively simpler than earlier concepts. Probably it's me not being able to refine the material relatively in a simple manner. Or maybe I'm making it harder. So keep proceeding as we are going. Don't give up. So things will get hopefully it will come together. Okay. Today, this week's chapter is going to be again relatively simple. It is again, you might have seen this in other courses. It is about a resistor. It's the second component among the three that we will be introducing, which forms the basic elements of an electrical circuit. So remember, I mentioned that there will be three electrical components. One is that the capacitor is defined by capacitance. And next, we will say today we will use the idea of a resistor. And third, we'll have a weight level that will be an inductor. I have introduced the capacitor by pointing out that it stores energy at this point, just to differentiate between a capacitor and an inductor. A better way to look at it is that it stores maybe energy, but just use the word electric energy. And that seems very trivial at this point because we have been studying only electric features. But you want to differentiate this with this stores magnetic energy. Or more precisely, this stores energy in the form of an electric field. So this is electric field with associated energy. And here we have introduced this yet magnetic field will be represented by the letter B. So it will store energy in the form of magnetic field. We haven't done this, that's just to give you a feel for what we are doing. So capacitor stores energy. So where do we lose energy? Most of the electrical energy that we lose is in the form of heat. Like when, or more precisely, when charges move around in materials, they hit things around and they bump into each other, and that loss of velocity is characterized by what we call heat. So this is mostly, we call it dissipation, which is losing energy. And that will be characterized by what we will use as a resistor. So that should give you a broad picture of what we are heading on to. An electrical circuit can be represented using three quantities. One stores electric energy in the form of electric field, another stores energy in the form of magnetic field, and the third is it's not that we get all the output from a source, you lose some energy, and that's resistor. It doesn't mean that every these components can be separated. Everything you see around, for example, when you connect a computer, very broadly speaking, this has a capacitor associated with it. You can, when you connect this to a battery, you can replace this with a capacitor and a resistor and an inductor. Every electrical component has all three properties associated with it. But most of the time, when you're designing an electrical circuit, we want one thing to dominate so that we can really control. If all three is there in all of them, then it gets harder to manage. So we do come up with electrical components which is dominant in one of the features, and that's what we're dealing with. Currently, we did capacitor, where the ability to store energy in the form of electric field was the most dominant feature. And now today, we will introduce the idea of a resistor. Doesn't mean that there is an ideal resistor there. Mostly a resistor has a capacitance associated with it, has an inductance associated with it. Also, all this is under the feature that there is a source of energy, which we say is the battery, right? So let's say maybe something is a battery, which is often pencil-like structures that you see in there, and most often, or here we are talking about constant voltages, a uniform voltage. That means to say that the battery, when we say is 9 volts, it gives 9 volts consistently. It doesn't change with time. This is called a direct. We introduce the idea of current, but this will be called just direct. It should be direct current there. So let's just say direct for the time being, because I haven't introduced the word current yet. There is another source of power. So let's say energy. I could call both are related to energy, and that is a wall outlet. At least in the wall outlets that we have around us, it is not a uniform voltage that you get there. It oscillates. This oscillates between 100 and is it 110 or 120? 20? Is the wall outlet voltage 110 or 150? 120, let's start. What? 110 to 120, okay, so I'm not completely wrong. It changes in different places, so what to be careful about that. Also, but it's also like between, let's say, 1 plus 110 to minus 110, and that's called alternate. Alternate, let me say current, and this is direct. This is often shortened into DC, and this is in. One of the reasons why we prefer to use AP, other than the fact that we have such a huge infrastructure that's already there, and it is easier to just stick with it, is that the power loss between long distance transfer is significantly less when we talk, say, about dissipation, right? Energy loss or something is significantly less than an alternating current. We won't be able to talk about that too much because alternating current comes at a later stage after we study inductor, and we spend very little time in there. But the main idea here is that all these features we are dealing with is talking about DC current. Whatever we are dealing is with DC current, but things get much more richer, much more if you think of it from exam point of view, it gets complicated, but if you think of it from modeling or application point of view, it gets a lot more richer when you bring in the time dependence in it, and the frequency, it's called the frequency dependence of these quantities, has a lot of application associated with it. So we won't be able to deal with that a lot. We will talk about it at a very later in the semester, for a week or so, but that's not sufficient to highlight those properties. Hopefully, you will see that in another course on. So today we want to talk about resistors, and before that, I want to introduce the idea of current. So let's think of a battery, that source of uniform voltage, and it is connected to at this point, a device, and for lack of introducing another component, I just say that a zigzag symbol which will represent a resistor. For time being, you don't want to say the resistor is just any device. Think of your laptop or your phone that is attached to a battery. And as we have seen that if there was a capacitance feature to that, it would the current, the charges will move from the battery into the device. The idea is that charges which are stored in the battery, they tend to move because this is a connecting wire. There's a lot of positive charges and the negative charges. Here, the positive charges want to come closer to the negative charge. They cannot cross the barrier, so they come through that process. And the idea is that in that process, you can get some useful work done by these charges. The moment they move, then we're talking about a time dependence and at what rate is are these charges going. So we want to talk about current is rate at which charges are moving. So it's pretty much like velocity. We talk about distance traveled by an object, but this is not a position dependent one thing. You say how many charges are going through a door, for example. Let's say you stand at the door and you ask how many people are going out, how many people are going in, and you count how many total charges per unit time. These kind of concepts, when it is not really dependent on the position itself, but just on one position, or going through an area is called, is what is called flux. And we will use that in a minute. So let's define current here. I, this will be charges per unit time. The charge per unit time. Again, a linear concept in general, all these features are not as simplistic as we talk about. It seems like I is really charge per unit time. In general, it's a complicated concept, but we will talk in the context of uniform charges going in a certain amount of time, or at least most of the things we will do will be uniform. Having mentioned that, I could say that the one of the circuits we will talk about here will have non-uniformity, and that will be called RC circuit. But most often we are working with linear quantities. This is the current. And let's say this can be also written as I is equal to charge per unit time. Often you want to write this as a differential statement. This is the total charge per total time, but if you take a small segment of time, then you're talking about a small charge. Also written as dq over dt. That will be an instantaneous if you want at a certain amount of time crossing a certain point. Both ideas are same. We have already used these kind of concepts when we said charge per unit area or charge per unit length. Those are all different statements saying that there is an associated definition in calculus associated with. Now let's think of a connecting wire. So this is a connecting wire, and we want to talk about what is the current in that wire. So this is a typical wire that we see around when you think of a computer connected to the wall outlet. There is a wire. This is one of those wires in there. So that's a wire, and what is actually moving in these wires? Often what happens is that there are positive charges which are fixed. These are positive charges fixed. That's not necessarily dependent on the material. If you had to think of at least in an ideal scenario, if you had a gas of positive and negative charges that are free to move, that will be also a conductor. But most often when we think of a conductor, we are thinking of gold or copper or aluminum. And in those materials, the positive charges are stuck to a place. They are the form of a crystal. So the positive charges are not mobile. It is the negative charges that are mobile. So these are fixed. And it is the negative charges that move. So that's negative charges that move. We put negative charges. And these move. So imagine a situation, all the positive charges are still, negative charges moving, and that's what happens inside a typical metal. You can think of a situation where both positive and negative charges are moving. There are models with that, but in our course here, we'll make it very simplistic that it is the negative charges that are moving. Even then, so if negative charges are moving in here, we should ask what is the that. So this is the velocity now, that's a motion, so that's a velocity. We need to ask what's the direction of the current. The direction of the current we talked about here is whenever we say current or charges move with the charges, we said positive charges moving in here. So negative charges could be moving this way, positive charges could be moving the other way. Both correspond to the same amount of current. So negative charges going to the right means the current is going to the left. That's the direction of current. So whenever we say current there is a current in a wire, it is pretending that it is the positive charges that are moving, even though in practice, most of the metals have electrons that are moving which are negatively charged. The actual motion of charges is opposite to the direction of the current. It is not a great deal of confusion from this point on. We will not point out that difference very much unless we specifically say that. And the idea is that there is current I. And the idea is that is a positive charge, even though it is a negative charge that is moving, we will pretend that it is actually a positive charge that is moving to the right. So electric charge moving to the left is equivalent to for all mathematical purposes, it is equivalent to saying that there is a positive charge moving in the opposite direction. We still want to define a model for this current in terms of, let's say if we have copper as the material in here, we would like to estimate at least to if not one significant digit, at least to 0 significant digits. What exactly how much current can we expect out of this? So let's think of current as really a charge per unit time. Let's charge per unit time. So let's say you have a filter in here and there is a sensor that really counts, and by delta Q over delta T in a certain amount of time, how much charge is crossing that particular plate if you want to stand there and really count the number of charges. It is hard to really count the number of charges, even though I said it in that manner. What is easier is we know what is the density of a material. That's what is more easily calculable. So what we know is that copper atom has a certain mass, and there are so many atoms per unit volume. So that density of atoms is known. And we might also know in one atom there are how many electrons that are really mobile. When I said that all the positive charges are not able to move, not all the negative charges are able to move. Typically in a metal, it's only 1 or 2 electrons that can move. So let's pretend that it is 1 electron in a particular atom that can really move, so that for every atom, that is 1 electron. So when we know that this is the density of the atoms, we know how many electrons are available to move. So we want to talk in terms of density instead of really the individual charges at that microscopic level, which is very hard to measure. So we talk in terms of density. So immediately we divide. So here's a Q over volume, and here we say there's volume again. So it is volume over time. Here's T. If we say there is 1 electron per atom, we can talk about atoms per unit volume. So let's write the statement as again, what is going on? Current is indeed charged per unit time, but often charges are not easily measurable. We want to talk in terms of some macroscopic quantity. By macroscopic, I mean something that can be measured for the material that we're talking about instead of the number of charges that crossing that particular line there. So we say current is equal to charge per unit volume. Instead we say charge, which is how many charges per unit atom, the charge per atom. I said let's think of 1 electron per atom. Sometimes it could be 2 electrons per atom, and the atoms, number of atoms per unit volume. And then there is volume itself, a cylinder. Cylinder's volume is area, cross-sectional area here. That's cross-sectional area A. And its length, let's say this is delta X. Right, so we are talking about volume as area times length. Divided by length. This is defined as N, the number density, which is the number of atoms per unit volume, that's N. Let's say it is equal to 1, is equal to 1 or 2. Typically 1 or 2. You could think of situations where that is all the way to 3 and 4 in a very most of the metals have this feature, and then there is area and area. So let me say, so this will be I would be equal to. Let me choose this. So this is the what I'm thinking. So that's 1 times N, and then there is A. And I will also, oh, when I say 1, this is 1 electron, right? So I have to write electron 1 for the charge. So it's 1 electron. So that's 1 electron number atoms per unit volume, that's the area, and we have delta X over delta T, the length. And that's velocity, right? Distance over time. Somehow we brought in the feature of velocity, which is not hard to intuitively think of. Whenever something is moving, you associate a velocity with it, and that velocity is a measure of current in principle. So it's the actual mechanical velocity that we defined earlier, and now that's coming in as in the definition of current. So this is often written as N E A and velocity. That's good. So again, this is so maybe I should define it right, right? So this is number density. And E is the charge carrier. Charge on the carrier, which is the electron. Which is the electron. A is the area. And that leaves us with the factor of V. And the way we have defined it, it seems like V is the velocity of the electron inside a crystal. If you take a metal, what is the velocity of the electron? And electrons move pretty fast inside a crystal. It's not at a slow rate. They move extremely fast. In fact, they almost approach the speed of light. They're really tiny objects. It's very easy for them to pick up speed, and they're if not 10 raised to 7, it's surely in the order of 10 raised to 6 meters per second. Extremely large speed. So let's try to. So this is going to be or let's ask the question as to what is this velocity. It seems like I'm only suggesting that it seems like this is the speed of the electron itself, but we will be surprised at this point. So let's just estimate our V here inside copper or a typical metal. So it is possible because current we know, let's say when we attach it to a battery, we know how much current it is. It's typically in milliamps. If you want to increase it, make it an amp, and at least have an order of magnitude right here. How many atoms there are in per meter cube? We have an idea. Electron charge and area. This could be a simple wire. We could say that this is about millimeter in radius, and let's try to estimate what is the velocity. that we are talking. So V here. And just to emphasize that this is not going to be the velocity that we're talking about, let me also introduce a subscript T here, so that I don't have to come back and change this. This will be called the drift velocity, I think, or speed of electrons. So how fast are these charges moving inside material, and we expect it to be large. That's our night interpretation, and that's equal to I over N times E times A. A typical current, so this is an order of magnitude calculation. So let's say 10 raised to minus 3, that's our milliamps. So it's 10 raised to minus 3. And oh, I should have pointed out here. Go back, then I introduce the term current. So that is I, so I mean the dimension for I, right? So I is charge per unit time, so this is coulomb per unit time, so that's second, that's the SI unit. So that's and that's so common in usage that there is a vocabulary for itself, and that is ampere. That's the dimension on a unit for that. Now we have always said that coulomb is the fundamental unit in SI units. It comes out with coulomb, but this changes between books often when it is more focused towards the practical side. It turns out to be ampere becomes the more common unit. So you can say that coulomb and ampere are both SI are both fundamental SI units, but in our course we will be using coulomb. So don't be surprised in somewhere else when you're working, you find that ampere becomes more fundamental. But the conversion is pretty straightforward. That is usually not much of a confusion related to that. And the short form of this is it. And that's what I was using here. The typical current that we get in an electronic circuit, whenever, or very simple way of saying this intuitively is that whenever heat is not a major issue in a device, you will see that the current consumed by it is low. Simple features are reasonably good smartphone or an electronic device. They are so tiny that the movements are really less. There are a lot of components, billions of components in it, but relatively they are so tiny that the movements are small. If the movement is small, movement by movement I mean real velocity of the charges, then the heat is consumed or heat released by it is very less. Think of other situations where you are really mechanically linked. The motor is an example. A refrigerator involves a motor, and there is also a real physical need for heat being transferred from one to the other. Wherever heat is involved, there is a significant amount of energy. And more intuitively speaking, whenever you have mechanical movements which are large, not microscopic, then most probably the current will be larger. A microwave is an example, refrigerator is an example, air conditioner is an example. Those are the things that consume a lot of energy. Light also consumes, relatively speaking, relative to your electronic devices, consumes a lot of energy in the sense that it is emitting heat. You need heat, actually, is always associated with light. So this is a milliamps, that's relatively small current. 1 amp is typically a normal current that is available in households. But milliamps is what is more common in electronic devices. So I've taken a smaller amount of current here. Current number density, how many atoms there are in a certain amount of space. That's Avogadro number is a representative of that. There are 10 raised to 23 atoms per centimeter cube. right? That's a standard. So think of a thumbnail that's 1 centimeter. You make a cube out of it. In that tiny box, there are 10 raised to 23 or anything typically for one significant or zero significant digit. There are 10 raised to 23 of anything that you can think of as far as atomic constituent goes in 1 centimeter cube. So that's 10 raised to 23 divided by this number per unit volume. So that's 1 centimeter. So let's convert this into meters. So that's meter, and then I have the cube. 1 centimeter, 1 centimeter, 1 centimeter. So that's your number. Density electron charge. We said that is 1 electron per atom. So we are doing order of magnitude, that is 0 significant digits, that's 10 raised to minus 19. So you don't have any significant number, only the order of magnitude is that. Area of a wire that we are talking about, these are tiny 1 millimeter and width, make it 5 r squared. 5 r squared, so that is already a factor of 3 and a millimeter cube. So that's 10 raised to minus 3 meter. I'm dropping the 5, so it's squared. So that's the area. So that should be the drift speed, and the expectation is that that should come out large, right? Because electrons are really moving fast inside of the material. So that's 10 raised to how do we do this? So 10 raised to minus 3, and when 23 goes up, that becomes minus 23. This is minus 2 into 3, 6, but it's in the denominator, it goes up. So that's minus 6 again, I suppose. Right, I think so. So minus 19 goes up, that becomes plus 19. And this is minus 6 again. So not this form maybe? Did I mess up? Oh, this becomes plus 6, right? Minus 3 decreases to the denominator, that becomes plus 6. So these two cancel out. And what we have is 10 raised to plus 19 and 26. That's about 10 raised to 3, 4, 5, right? That's okay. So 26 minus 19, so that's 10 raised to minus 7. And that's the velocity per meters per second. That's really small. We wanted something of the opposite of it, right? So we wanted 10 raised to 7 meters per second. That's the speed of light. But this is really small. Like we are talking about, this is about less than about micrometer. That's 10 raised to somewhat micrometers per second. At this rate, if we were to switch on a current, like what we are saying is that there is an electron that starts from here. This could be the source, let's say a battery, and this could be your device. By the time it reaches that, if this is about 1 meter, that's going to take about velocity is so small that will take about 10 raised to 7 seconds. 10 raised to 7 seconds is about how much? That's about a year, right? 1 year is about 10 raised to 7 seconds. Again, to 0 significant digits. So you're saying that electrons take about 1 year to go from one end of the battery to the device. That's again not intuitive, but that's actually true. And how you want to interpret is that these electrons, they are going very fast. They're almost going at the speed of light, but they keep hitting onto the crystal atoms. So every time they move even a millimeter or not even a millimeter within an atomic distance, within 5 atoms, they come and hit onto something, they go back, they again go and come back. So in that zigzag motion, they hit here, again go back, and in that zigzag motion, they're getting an effective speed of only that tiny amount. Right? That's a really small speed, and that's why you call it drift speed. Even though the electrons are moving fast, they're drifting, effectively speaking, at a very slow rate. Then it might lead to it might lead to a issue that how come that you switch on your light or on or off, you almost instantaneously the the bulb goes off. How come the electrons are going to be able to reach that path? The main idea is that it is not one electron that is moving, it is the idea of flux. We are not talking about one electron, it is the flow of electron that matters. Think of a or a water tap in your kitchen. When you open the water tap, it's not that the water has to come from the tank to there. Water is already at the tip of the tap. When you open it, it just has to flow. It is a flow that you have begun when you open the tap. It is not that a particular atom has to move from the source to that tap. So similarly, in this wire, there is already a lot of electrons in there. This electron has to serve the device. It's just a flow that you begin. It is the idea of flow that matters, and that flow is called a flux. So current in many ways. So current, even though we define it as charge per unit time, that is a very convenient concept that is when it comes to homework and all the equations that we will deal with, it is very convenient to use charge per unit time. How many charges are crossing a particular point in the pipe, how many charges are going per unit time. But current is, I think of it as a flow. So think of it as flux. That word is flux related, associated with to flow of charges. So it is a charge that is flowing from one point to the other, and the flux associated with it. Flux has to do with area. That means to say that you stand at the door, so that means you have to introduce the idea of an area there, and that's what is that's what will come in more handy as you proceed later on at a concept level. But for our purposes, it will be sufficient. You will see that we will be working mostly with linear quantities. Current will be just charge per unit time. So that's introduces the idea of current, and for our purposes, what we will say is that whenever you connect a device, this is any device. When it comes to infusion, think of any device. And when it comes to your model or your for specificity, what this means is a resistor. The idea of a resistor is going to consume energy. This is a source of energy that consumes energy, and we talk about how much energy it consumes. And we want to talk about how many charges are going through. So remember, the charges are just passing through the resistor. They don't get stuck in there. Unlike the capacitor, the charges do not get stuck. So they just keep moving. So the way we want to, it's good to have an analogy in that context. Gravitational. So again, since we are talking about a flow, a water flow helps to give an analogy. So this is gravitational analogy. And the idea is you have, let's say, that's your muscle, so that it's someone standing here. That's ground. And this person lifts masses. So this is mass M, and lifts it and put it there. So that's change in gravitational energy. You pick a mass and place it at a higher distance from the center of Earth. You have spent or you have stored potential, gravitational potential energy in the mass. So that's the job of a battery basically. You lift a charge from a lower electric potential and place it at a higher potential. That's the job of this battery. It picks, it is neutral here. It plucks a positive charge and gets it separated from a negative charge places it here, higher potential, lower potential. Same thing, what is this person doing? Pick a mass M from a lower gravitational potential energy, keeps it, lifts it to a certain height, to a higher gravitational potential energy. And now suddenly it has the ability, if this energy was released, it will have movement. So if we keep going, so it is that height does not matter. So this does not change its gravitational potential energy. At this point, it can fall here, and as it falls, it gains kinetic energy. Here it is gravitational energy, higher potential energy. I have gravitational potential, here it is lower potential. But as it comes down to a lower potential, it will start moving. That movement is what at a microscopic level, we want to convert that into a very average quantity, and that's what a temperature. So this is velocity, v, speed, and when things move, that will be for our purposes very simplistic, will be temperature. The more motion of atoms and very microscopic electrons and protons inside a material at a very broad level is what will be associated with temperature. And if the temperature increases, that's basically saying that you've lost some energy in the form of heat. So for our purposes, this will be heat. So a mass comes here, you lift it up, you fall, so this could be a waterfall, right? So there's a waterfall here. It can be used if you can use this energy, use this temperature to do some useful work, that's good enough. But if you cannot, it comes down here, and again you can move it. If no energy is lost in temperature, this can go forever. Right? If there is no energy lost at all, so the charges will keep moving, and the same idea here, the charges move, but usually there is an amount of energy lost in this form, some amount of velocity could be used for useful purposes or sometimes useless purposes also. We are not able to capture that energy, and that's basically what is happening. So a battery moves charges from a lower potential to a higher potential, and then you let that charge move from the higher potential to a lower potential through your device, and the hope is that we can get some useful work done in that process. And this process will be characterized by an equation by us, and it will be a model. And most of what we are doing is an approximation. It's a linear approximation of what happens in reality. So all this will be really approximate quantities. But having said that, I should also point out that most of the time when we are working with mechanical motions in the first semester, there was one limitation that the acceleration due to gravity comes into most of the equations, and G there was 9.8 meters per second squared. And this is known only to 2 digits. If you want to make this more precise, then you have to really to take care of a lot of other factors. So usually we do not know that. So mostly that becomes a limitation, and even otherwise there are most of the sensors that we have for mechanical devices, but they are not accurate enough. So usually to get 2 significant digit accuracy in an experiment is hard in mechanical devices or in mechanical configurations. But in electrical configurations, it is very easy to get third order. You can go to third significant digit, and you can really get good good validity for the equation that you are using. So even though we are working in very approximate linear approximations that we call here, nevertheless, when we go and measure things, it comes out very well, and most of the time, the energy lost in electrical quantities is relatively smaller, so it is worthwhile to go through this linear approximation. So this brings us to the idea of what is how much current is actually passing through a device. You want to have a model for that. So you would like to ask if you have a battery B and you have a device which is represented by the resistor R. So you connect this, and what happens is that charges start moving. This is the storage of charges, and the moment you allow it to move through a conductor, all these positive charges want to come near the negative charges, so there is motion of this charges if you want, which is what is current. And we will represent that current. Remember, current is represented as going or the motion of positive charges, even though inside a metal it is the negative charges that are moving. So this is the direction of current here. So that's current I. So what is the system doing? We connected a battery of voltage V, that's a 9 volt, and the device had a resistance R, and the system decides how much current is it's going to allow, current is going to flow through that device. So this is the effect, and this is the cause. You have assembled the circuit, that's the cause, and that's the effect, and you would like to have a prediction for it, and a reasonable model for that, a linear approximate model is V. It is proportional to the voltage. Higher voltage you apply, larger is the current, and it is inversely proportional to the resistance. So that's a model that we will have, and that's what is called Ohm's law. In this way of saying it, it seems like resistance is really a quantity associated with a device, like capacitance was associated with a certain device, how much energy it can store. In here, it seems like resistor is a resistance here is a measure of I. So I need to define this quantity. So earlier I said it's a resistor. So R is the resistance. That's a physical property, the resistance of a resistor. Its unit would be, so unit of R would be, move it to the left, so it will be volt over ampere. That's good enough, but as I said, resistor, capacitor, and inductor forms three of the basic components of an electrical circuit. So that's too much of effort you put in when you have to repeat it every other moment that there is volt per ampere. You get lazy, you create a vocabulary for it, and this is ohms. Ohm. That's ohm. And the symbol for it is not ohm, it is the capital. That's not sigma, right? Capital omega. Yeah, thank you very much. Yeah. Capital omega. Yeah, that's a Greek letter, capital omega. Okay, so that's resistance. What is the typical resistance? It's good to be aware of what are the standard resistances that you come across. Anywhere between 100 ohms is, or 10 ohms, let's say, is a low resistance in standard by standard electrical devices. In electronic devices, since they get really tiny, That's the difference in electrical one. Talk about electrical devices. 10 ohms is low and about 10 raised to 6, that's a million, right? 10 raised to 6 ohms is high. A resistance in many ways is also a measure of how good a conductor is. If you have a large resistor, this is more of an insulator. And a low resistance is more of a conductor. If you were to connect yourself to a battery, let's connect ourselves to a 9-volt battery, not to a very high voltage, then you can talk about what is the resistor. We are reasonably, unless we are having a lot of sweat on us, there is a lot of most of the time, remember that current goes through the outer surface, unless we penetrate, like there is a lot of liquid in our body, but presuming that you're not piercing yourself, then our resistance is large as a body resistance that's generated. That's very vague analogy. Better is that if you have to actually connect the material, that's a better, well-defined quantity. And a typical wire, a copper wire, will have less than 10 ohms. So that's a very good conductor. At high resistance, if you have an insulating piece of plastic or something, that will be very high. It won't even be 10 raised to 6. It will pretty much cross, let's say 10 raised to 10 or something. But a human is somewhere in between, and it comes out around 10 raised to 6. So that's your current, resistance, and voltages. And now immediately we would like to have circuits associated with it, but a small digression. I would also like to say, what does the resistance depend? Like again, in a linear approximation, these are not exact at all. These are models to a linear approximation. How much is the dependence in this? If you have a metal, so this is the resistor. What does it depend on? If you take a simple material of wood or copper, what really characterizes the fact that it has high resistance or low resistance? Typically, if you have a wire, let's say, that's wire, that's area A, and let's say this is length L. The length L. And it is made up of a material. So there is a material property, length. So geometry is the length and area, and the material property is what we will define in a minute. So resistance will be, it is pretty much associated with resistance to current or resistance to the flow of charges. The charges would like to flow from one end to the other, and there is a resistance to that. And what does it depend on? Think of this is a corridor in this building, and if there are a lot of atoms in there, a lot of positive charges in there, and if electrons have to move around, the charges to move around, it bumps into each other, and that's a sort of an analogy for resistance. So it depends on if it's a longer length, larger resistance. It's proportional to the length L. And cross-sectionally, again, you're walking through a corridor. If the corridor is really thin, then it will be harder for you to go through a crowd. So that's pretty much a way of visualizing the motion of charges inside a wire. So there are a lot of positive charges, and it has to squeeze through in there. So if the area is large, resistance is small, so it is inversely proportional to area. So it's proportional to the one of the geometrical parameters, the length. It is inversely proportional to the area. and it is proportional to the material property, and that we capture in what we call as rho. So this will be resistivity, so that's the rho. The Greek letter rho, I think, that's how it's pronounced. Rho. So that's rho, so this is resistivity. Of the material. So resistance can be captured into two geometrical parameters and a material property, and that's will be an expression that will be used. So whenever you want to think of resistance, think of it as rho L over A. And again, the linear approximation in a more complicated system, suppose you have a sphere, like linear approximation, what I said is that this is actually having a length and an area, and this is long enough. These things immediately break down. If you say that you're connecting a wire like this in a sphere, then that's not linear, then suddenly that's a spherical object that you brought in, and you have to bring in other factors in here. So this is a simplistic model, and in that particular model, you have resistance given in terms of having introduced the resistance like we did capacitors, we would like to build circuits associated with it. And in this case, we will stick to just having resistors, either have two resistors in series or in parallel. And then next time, so in the next lecture, I'll bring in both a resistor and a capacitor together. Right, so that will be the first time we will have a reasonably non-trivial electrical circuit that comes in. And immediately you will see that the calculus comes in, and we will write down the first differential equation that's necessary to solve. Let's say resistors in series. We have one battery, and we connect it to two resistors. Think of two devices if you want. These days, phone seems to be the most accessible quantity, but usually, at least historically speaking, light bulbs were the most common features, most common electrical devices that you saw around. So you say this is one bulb, that's another bulb, and how much energy is consumed by that. But phones are good representation. So that's one device, another device, and you would like to ask how much current is pulled by this resistor. Remember, current, I said, is a flow. Right? Whenever you think of it as a flow, how much ever current goes in here has to come out of that. Like positive charges to negative charges, the number, the current itself does not change, but in the process, it might lose energy. That's a different scenario. But the current is exactly the same in the same wire. It's like a pipe, water pipe, water hose. How much ever water goes in has to come out of that. So we will often talk about I1 and I2, and if it is in series, that has to be the same. You say this is current I1, and that is current I2. So using the idea of a flow of charges, the flux of charges, I will be equal to I1, and it is also equal to I2. And I is the amount of current that is being pulled out from the battery, that is V. So that's first relation. This is the equivalent of the capacitor that you submitted a homework on. You talked about charges Q1 and Q2, and we talked about what is the connection or what is the relation between the charges in series or in parallel. This is the relation between the currents and in resistors and series. The voltage itself, this is a high potential, low potential. You can say it is plus 9 volts here, 0 volts here, relatively speaking, there is a potential difference of voltage V. This voltage is the same at this point because that's a conductor that is connecting it. Across a conductor, the potential difference is 0. So this is at a higher potential. This is connected to this point. That's at a lower potential. As we go from here to there, the potential gradient has to come in. So these two will have different potential. So let's say across this, by the time we go from here to here, the potential drop, this is the language, the potential drop is V1. Potential is usually across two or about 2 points. And that's the drop across the resistance R1. And this is the drop across resistance R2. That's your V2. And this drop, total drop, V1 and V2 should be the same as the drop from here to there. Because that's the same thing. Like whether you cross this barrier or you cross that barrier, it's the same 2 points you're coming across because it's the same wire that is connected in there. So the potential difference between this and then that end, if you want, is the same as V1 plus V2. And next, you would like to ask if these two are correct. You would like to talk about an equivalence circuit. So again, think of it as cause and effect. You have constructed this configuration, and because you have constructed this configuration, there is an amount of current that flows through it. Current is the effect, and cause is that you connected these two resistors to the voltage V. What if you had connected a single resistor and you ask what should be that single resistor? So the same current, you want to pull the same amount of current from the same amount of same amount of potential difference V, and you ask what is the resistor, what's the single resistor that you would like to connect there, and that's an equivalent resistor for the two resistors in series. Exactly the same idea we introduced in capacitor. So for that purpose, now this is V is equal to IR. So we have V is equal to IR. There's only one piece in there, one resistor, so that's IR. That's our Ohm's law. And here we have V1 is equal to I1 times R1. And V2 is equal to I2 times R2. That's for individual resistors, always this is true. That's Ohm's law. For every time you see a resistor, the voltage drop across that particular resistor. Always a local phenomena. I2 times R2 is V2. I1 times R1 is V1. I1 times R1 is not equal to V. Sometimes it might be, but in this case, it's not. So you have these three relations. And substitute this quantity here, so I times R equivalent is equal to I V1 is so V1 is equal to I1 times R1 plus V2 is I2 and R2. But I is equal to I1 is equal to I2, so I can cancel them out. So I is the same as I1, is the same as I2. It seems like algebraically wrong, but they are all identical quantities because I is equal to I1 is equal to I2. So that cancels out, and I learned that the equivalent resistance is equal to R1 plus R2. So the resistors in series add. I want a single resistor to be connected instead of two resistors in series. They add. This should be contrasted with that of a capacitor. Capacitors in parallel act. Resistors in series act. So there is a distinction between the two. They're exactly swapped in a sense. So that's your equations, and in your homework you will talk about really how much current is going through an individual resistor. We said that resistors, the idea of a resistance is to consume energy, how much energy it consumes. So it is good to have a feel for how much energy is being lost in a resistor. And since we are talking about a current, there is also a time component to that. So instead of talking about energy itself, we will talk about power. Power, remember, is energy per unit time. How much energy is consumed or drawn or created per unit time. So power, power P is equal to energy per unit time. Energy is voltage times Q, so very broadly speaking, so this is V times Q over P plus V times I. So you multiply the current and the voltage together, you get how much energy is lost per unit time, and that's the idea of power. So power is equal to energy per unit time. The power is current times voltage. Replace V with I, that's also I square R, or it is also V square over R. Either way, like a capacitor, you can either talk in terms of charge and capacitance, or you can talk in terms of voltage and capacitance, or you can talk in terms of V square, half C square of or capacitance times voltage itself. Right? So that's tells you how much energy is lost per unit time. In the last 3 minutes, should I attempt on doing resistors in parallel? I think yes, yes. Yeah, so it's set in the homework, so maybe it will help. Let's go fast. Resistors in parallel will be, you have a battery, you connect it to a resistor R1, and that's R2. That's voltage V. Notice, think of flow. Current is a flow of charges. There is a current I that comes out of this, but now it gets split. Some of it goes through R2 and some of it goes through R1. So that's I1 and that's I2. But what is true is that this flow is bifurcating from a point. So the current distributes. I is equal to I1 plus I2. Voltage is the same. Potential difference between these 2 points is the same as this point, as the same as this point. If the drop is the same because they are all connected to the same conductor. And the potential difference is exactly the same. So voltage V is exactly equal to V1 is exactly equal to V2. If that is the case, you put in a equivalent resistor to that, R equivalent, and you say that V is equal to I times R equivalent. That's I. This time the same I will go in this. Replace current with voltages, so you have V over R equivalent is equal to V1 over R1 plus V2 over R2. But the voltage is cancelled because V1, V2 are the same. This cancels out, and we learn that the equivalent resistor and parallel is the sum of the inverse. So those are the characteristics that is needed for parallel resistors and parallel. I went in a hurry, but we will come through this again next time, where we will connect this, we'll make this compound, and we will see this again in there. Thank you very much.